Okay, recording's on. I think we can get started. Awesome. So thanks so much, everyone, for joining for the session 2 of Quant Finance C++ online. As I mentioned earlier, this session is a continuation of the first session, which was on shared pointers a couple of weeks ago. There's pretty good feedback from the session, so I'm quite excited to continue going with these sessions. Before I dive into the shared pointer, quick overview of the community, why I created it, what the goal is, and then a quick recap on what a unique pointer does, and what was discussed in the previous session. So regarding Quant Finance C++, the main goal of creating this community was that I think the C++ in finance and where people don't really discuss some niche techniques and some important aspects which are not really some important aspects of technology which are not really considered in other industries. And there's no real reason for this. I think like for the secrecy, there's no real reason. So I just wanted to create a community and get some things going, discuss more of how C++ works in the quant finance world and what specific parts of the technology are important. And so, yeah, I think discuss C++ techniques used in quant finance, how to get into the industry and progress in the trading industry and make tech and trading a bit more open space. So quick overview about me. I'm a tech lead at Maven Securities, which is a high-frequency trading firm. I used to work in the London office before, which is the headquarters of Maven. And then I moved to Chicago a couple of years ago. I'm interested in finance, low-level programming, and C++. No cookies for guessing that. All right, with that out of the way, let's dive into the actual session. The reason we're so as I mentioned before, I'll do a quick overview of smart pointers, recap what we did for stood unique pointer, and then dive into how a shared pointer is implemented. Things like these about how a unique pointer and shared pointer are implemented they're not really so someone asked me a question in the Google form for the meeting that why is it important to know how a shared pointer or a unique pointer works under the hood. Is the idea that we're going to be implementing our own pointer and using that instead of the standard library container. And no, I don't think that's the idea at all. Where possible, in fact, unless like Boost or some other third-party library provides a better container, where possible, I try to use as much as stood library containers as possible. The reason it's quite important to understand how these work under the hood is to know whenever you're writing a stood shared pointer or a stood unique pointer, what is the cost associated with that container. For one, we need to differentiate when to use a unique pointer versus when to use a shared pointer. And secondly, whenever we use any standard library container, it's quite critical, especially in industries like trading, where performance matters quite a lot, or like gaming industry, for example, as well. It is quite important to know whenever you're using a container, what the cost with that container. That cost could be both in terms of compile time cost or an actual runtime performance cost. So that's the reason it's always a good idea to implement these containers on your own, just to analyze how they work under the hood. And they're also pretty common interview questions. So I've known people, and when I was interviewing as a graduate, there were a lot of firms asking how to implement a unique pointer, and then a following up question, how to implement a shared pointer. So yeah, that's the overall idea. Let's do a pretty quick overview of smart pointers. So as I mentioned in the previous session, why do you use smart pointers as opposed to the raw pointers in C or C++ as well? The primary advantage of using smart pointers is that they provide automatic memory management, something called as resource acquisition is initialization. What it basically means is that whenever your pointer goes out of scope, the memory associated with that pointer, if there is any memory associated, will be automatically deleted. and I'll talk a bit more about this in the next slide. There are some other advantages as well as compared to raw pointers. There are multiple types of smart pointers: unique pointer, shared pointer, and weak pointer. I'm not going to be talking about weak pointer, but just considering unique pointer and shared pointer, just by using a specific smart pointer type, it introduces clear ownership semantics. So when in code you see someone's using unique pointer, that implies that the memory has a single owner, versus when someone's using a shared pointer, that implies that memory has shared ownership. But this is not very clear when you just use raw pointers. So that's a pretty good advantage. It makes the code more readable, more maintainable. And the last one, which is kind of similar or like more of a effect of the first one, which is automatic memory management, is exception safety. So if you're using a raw pointer, and say on like line 1, you've initialized the raw pointer with some memory int star I equals new int 42, and then on line 10 you're deleting that pointer or like freeing the memory associated with that pointer. So anywhere between line 1 and line 10, if an exception is thrown, now you've got memory associated with your pointer which was not freed. Automatic memory management basically means whenever the pointer goes out of scope or there's an exception thrown as a result of which it does end up going out of scope, or like the stack ends up getting unwounded, the memory associated with the pointer is going to get freed. So it is kind of related to the first point, and as I mentioned, I'll talk a bit more about it in the next slide. So talking about automatic memory management, or how it's achieved using RAII, what it basically means is that the resource ownership is tied to the object lifetime itself. Resources are acquired in constructors and released in destructors. So consider this example where on line 3, there's a pointer to an integer. You allocate some memory on the heap and assign that to the pointer. And then on line 8, you delete the pointer. So as a result of which, the memory is going to be freed. On line 5 and 6, if you're checking some condition and returning as a result of it, if the condition is true, when the condition is true, this is going to lead to a memory leak, because like you're going to return from this function, the stack is going to be unwinded, and then the delete statement is never going to be called. This is leading to a memory leak. So although your pointer goes out of scope on line 6 when the function is returned, it does not really free up the memory. RAII is actually a very simple concept to implement. In the constructor, you allocate, or in the constructor, you assign the memory to the pointer, and in the destructor, you delete the memory. So in this case, you can see this int RAII container. All it does is that on line 3, it takes a pointer. In the constructor, it takes a pointer to the int, assigns it to the data member in the class, and on line 4, there's a destructor that deletes the pointer. And we can use this container in the same code that was there before. So on line 3, if you use this container, on line 6, if there's a return statement due to the condition being true, it's simply going to call the destructor because the object is going to be destructed, and as a result of the destructor call, the memory is going to be freed. And same case with exceptions. If there's an exception thrown, the object is going to be deleted and the memory is going to be freed. So that's what RAII is. It's a pretty smart concept, but also very easy to implement. Okay, so quick recap of unique pointers. Unique pointer is one of the smart pointers that was introduced in like modern C++. I think C++ 11 or 03, maybe C++ 03, maybe not sure. Probably 03. Anyway, so unique pointer is a smart pointer that owns and as a result is responsible for and manages another object via a pointer and subsequently disposes goes out of scope. So very similar to what we just saw in RAII. On on constructor, it assumes ownership of the object, and on destructor, it disposes that. What's unique about the unique pointer is that it can only be moved and it cannot be copied. And I'm not going to go into the implementation details in this session. You can check out the previous session for that. But we have the implementation details on the slide here. Did that in the last session. So how does a shared pointer work as opposed to a unique pointer? And before I dive into the shared pointer, just a quick check. Anyone has any questions on RAII or just the overview of unique pointer? I'm going to wait 10 seconds to see if anyone has any questions. Okay, if not, that's right. I think that's a good sign. Last session was all about RAII and unique pointer. So let's get started with the new things for this one, which is a shared pointer. This is as per CPP reference. Shared pointer is a smart pointer that retains shared ownership of an object through a pointer. Several shared pointer objects may own the same object, and the object is destroyed and its memory deallocated when either of the following happens. So the first condition when it's going to be destroyed is that the last remaining shared pointer owning the object is destroyed. And the second condition is that the last remaining shared pointer owning the object is assigned another pointer via the operator equals or reset. So if we ignore the second condition for now, the first condition is pretty simple, or like pretty similar to how a unique pointer works. In a unique pointer, there's no shared ownership. Only a single unique pointer is responsible for the lifetime of an object. But in shared pointer now, shared ownership is introduced. So an object or a memory can be associated with multiple shared pointers. When you start off and assign that memory to a single shared pointer, that is the only pointer that's pointing to the memory. And then if you assign that, or like if you copy the shared pointer, what happens is that just the reference count is incremented, which implies that two shared pointers are now pointing to the same memory location. This is not even possible in a unique pointer. A unique pointer is not copyable, whereas a shared pointer can be copied, but it's not like a deep copy. It does not actually copy the underlying memory. All it does is create another pointer pointing to that memory. Now, say the second pointer, or say now the first pointer goes out of scope. Instead of the first pointer deleting the associated object or the associated memory, it just goes out of scope. And the memory remains there until the last remaining shared pointer owning that object is destroyed, which is the first condition. And second condition, when we implement shared pointer, we'll see that assigning like the assignment operator or reset, like the assignment operator basically assigns the current shared pointer into a different one. So now it's owning to a new memory location. So the existing memory location may be destroyed if the reference count is 0, and reset is similar. So let's get started with an implementation. Quick overview from a CPP reference. Oh, I think it's only showing my slide. Let me change the screen sharing. See if we can do this. Okay. Can anyone confirm if this is big enough or too big, too small?
No, look good.
All right. Thanks, Petra. Cool. So let's have a quick look at what methods are implemented in a shared pointer. But before I do that, you can see shared pointer has this templated, like shared pointer is a templated class. Oh, it's since C++11, not L3. That's good to know. Anyway, class only templated on type T. This is a bit different to unique pointer. So if I open up the unique pointer here real quick, there you go, unique pointer here. So it is a bit different to unique pointer where if you're looking at the first one, unique pointer has the type T, but also the type of the deleter, which shared pointer does not have. I'm not going to go into the details of the difference right now. We'll see it a bit later towards the end if we have time after the basic implementation. But it is something to keep on the back of your mind that unique pointer is the type of deleter as well, whereas shared pointer just have the type of the pointer. We've already discussed about all of this. So just having a quick look at the member functions. So it's got like a bunch of constructors, operator equals, which we just discussed, reset, which was also discussed a bit. But moving on, it's got the classic observers get, which returns the pointer, the arrow operator and the asterisk operator. And then one method which is unique to shared pointer is use count, which returns the number of shared pointer objects referring to the same manager object. As I discussed, a shared pointer basically shares the ownership of the object and stores a reference count internally in order to correctly deallocate the object. So we need some sort of account to keep, like we need some sort of account which is shared across all the shared pointer instances. And whenever a shared pointer goes out of scope, we decrement that count. Whenever a new shared pointer is created or copied, we increment that count. We'll see a bit more on the details soon. Another function which is unique to shared pointer is unique, which checks whether manage object is only managed by the current shared pointer object. You can probably already guess that this is pretty simple to implement. If we already have a count, we are returning the count in use count, and then unique is just checking if the use count is equal to 1. Yeah, and then similar to the unique pointer, there's a make shared, which creates a shared pointer that manages a new object. Although make shared is more interesting than unique pointer, we are definitely going to talk about this a bit later. So let me quickly open up a skeleton of the implementation, and we can get started with the actual implementation from there. All right, so here I have like my own namespace, CPP Online, in which I've got a shared pointer. So since this is in my own namespace, this differs from the standard library shared pointer. And I've got the skeleton here already. The constructor, this is constructor. Then the destructor, copy constructor, move constructor, copy assign, move assign. And another quick note, the copy constructor and copy assignment were simply deleted in unique pointer, but in shared pointer, they are present, obviously. And then I've got another constructor with null pointer and assignment with null pointer. And use count, I don't have the unique function here, but as I mentioned, it's basically just returning unique use count and some getters, which is the asterisk operator, arrow operator, get, and the operator bool. Okay. Yeah, let's just get started. So how the constructor is going to look like. This is pretty simple. I've got a data member here, which is mptr, and all the constructor is empty arguments or the null constructor here basically do the same thing, which assign my pointer to null ptr. And in fact, as you can see on line 36, it is initialized with a null pointer. So I don't even have to do this. I can simply just keep it like this, or maybe make it equals default, which should just work fine as well. And similarly, constructor with null pointer does not really have to do anything. So let's Actually, let me move these here because they are more related to the default one. So that's it. I'll come to the assignment just in just a minute. But let's look at the more interesting constructors, which is constructor with a pointer. So constructor with a pointer, as you can guess, is simply going to do simply going to assign the pointer data member to the incoming pointer, and that's it. The destructor, I think this is where now things become a bit tricky. In the unique pointer, because there is no shared ownership, all the destructor does is delete m pointer. And even if it's a unique pointer, calling the delete method on a unique pointer is safe. It does not lead to undefined behavior or anything. But this is where things start getting a bit tricky. Shared pointer can, two shared pointers can point to the same memory location. And what we want to ensure is that when a shared pointer is destructed, the memory location is only deleted when no other shared pointer is assigned to it. So imagine I have, okay, this code is not going to compile, but let's say I have something like this. I have shared pointer sp1, a shared pointer of type int sp1, which is pointing to this integer, and then I have shared pointer of type int sp2, which is constructed from sp1. Now I've got two shared pointer pointed to the same memory location, which is this location. And then let's say what I do is take sp1 out of, I mean, it's not super trivial to have sp1 out of the scope here without sp2 being out of the scope, but let's say I call some function foo, and I move sp1. So moving sp1 is basically going to should move is different to should copy. In here I'm copying where sp2 is now also going to point to this new memory location, so the reference count is going to increment. But what move does is that it basically takes the ownership of the object from sp1 and passes it on to a different pointer. So let's have some point foo here, which takes shared pointer as well. Okay. So now I've got sp1, which is I've moved out of sp1. Moved when an object is moved, we can no longer use it, or should no longer use the members inside that object. And I've only got sp2 pointing to the integer. Now the tricky part is that when sp1 goes out of scope or is moved from, we should not delete the actual memory that is associated with it. It is only to be deleted when all the shared pointers pointing to that memory go out of scope or are reset or moved from. So simply deleting in the destructor is wrong behavior. I somehow want to ensure only delete when no shared pointer is pointing to memory address at m pointer. So how do we do that? I mentioned it a couple of times now that shared pointer not only maintains the pointer, but also a reference count. So let's add a reference count here. Unsign mref count. And let's initialize this with 0. Okay, so our default constructor, I think, is still fine because it points to a null pointer. Null pointer is not an actual memory. So the reference count should still be 0. This is fine as well. We need to change this a bit, where now I'm actually pointing to a memory location, and my mref count should be set to 1 if this pointer is not out. So I'll I'll do a null check here. If pointers equals null PTR, then keep it 0, otherwise make it 1. So on construction, if it's a valid to some memory, I'm incrementing the ref count or assigning it to 1. Now destruction is simple. All we want to do is if my ref count is, or actually, the first thing we want to do is decrement the ref count if the shared pointer was pointing to an actual memory location. So let's check our member pointer. If member pointer is not null, and I can basically make this a bit more concise by just checking if member pointer, decrement my ref count. And now if the ref count, so we are only deleting the actual memory if the ref count is 0. But to note here that the member pointer in the class should always be assigned to a null pointer. Like, although deletion of the actual memory only happens when the ref count is 0, we do want to assign this to a null pointer, because otherwise it's going to, like, if you don't assign this to a null pointer, it's just going to hold a dangling reference. So this is important here. On to the other constructors. Quick question. Does anyone see any issue with my reference counting here? Can anyone foresee an issue? Yeah, this is not going to compile as of now, so I'm going to comment this out. Okay, so my question is that, yeah, I'm sorry.
Is it a thread safety by any chance?
No, let's say there's a single thread.
Okay.
But it is an issue as well. But let's say for now, we're writing a single threaded shared pointer.
So multiple objects will have different reference counts. So
yeah,
they won't. One object will have no idea about the share count of how many objects are sharing the same memory location.
Yeah, exactly. That's completely right. Oops. So consider this case now. I've got this pointer which is pointing to some shared memory location, and then the ref count in my class is a local data member. So each new class is going to have its own reference count. So if I make like, again, in this case, it's not going to compile yet, but if I make shared pointer 1 here, sp1 now has sp1.mref count. It's now equals 1. And when I copy this, the sp2's ref count count inside the shared pointer 2 is a local member. So although on copy I can assign it to 2, but each class is holding a completely independent reference count. So now I've got 2 objects, but then if I further mutate sp2 and create like a third object copied from sp2, like let's say I further do this, sp3 equals to sp2. Now at this point, sp3 has access to sp2's like on construction, sp3 has access to sp2's reference count, and it can assign its own reference count to 3, because sp2's reference count will be equal to 2, but it has no relation with sp1. How is sp1 going to increment its reference count? What we want to achieve at the end of this is that all of sp1 to 3 have a reference count equal to 3, and that is simply not achievable because the reference count is a local data member now, which is like local to each shared pointer object. So what we want to do instead is have this reference count shared across all the shared pointers pointing to the same memory location. And how we do that is, instead of making this like a local object, make this a pointer as well. So let's make this unsigned, a pointer to unsigned, and this will be a null pointer Or actually, instead of a null pointer by default, maybe we can start off with points to the 0. Basically an unsigned pointer, which is defaulted to 0. I think we can do this instead. Now, as soon as I did this, there is one important thing to note. I guess question to everyone: is there a runtime, like before it was just a reference count assigned to 0, like a normal standalone member in the class. But now I've created a pointer which initializes to the value 0. Is there a difference at runtime between the previous approach and this approach?
Is it the heap and the stack thing? Or you would have to unallocate the memory at line 47 now?
Yeah, exactly. So that is one really important difference to note, that on line 47 now, even if you're storing like a null pointer, it's going to allocate memory on the heap, which is again a runtime cost. This is like one of the reasons why you should know how the container works under the hood. So I think it's not ideal that it allocates memory even if it's pointing to a null pointer. So let's just assign it to a null pointer right now, and then later we can allocate memory for the reference count. Okay, let's revisit our constructors so far. The default constructor remains the same. This is fine as well. Now the constructor where it's being assigned a pointer, what we want to do is, if the pointer is null, then keep this as a null pointer. But if the pointer is not null, then I want to create a new reference count, which is equals to 1. Now in the destructor, the contract of this class is that pointer, whenever the pointer is non-null, the ref count is also going to be non-null. So I can either check the pointer count, it's just safe code because that is how we are going to be implementing it, or it's going to be an implicit like contract in our code. But yeah, basically to make it a bit more obvious, instead of the pointer, let's check the reference count here. If the reference count is non-null, what we want to do is we want to decrement the reference count. Oops, decrement minus star and ref count. So we want to decrement it, and then we want to check if it's equals to 0. I want to delete my pointer. Actually, I want to delete both my point count as well, because that also is a heap allocated object. And then let's assign the pointer to a null pointer, and then ref count to a null pointer as well. So far, so good. Anyone has any lingering questions on this? Okay, awesome. Let's move on to the more interesting constructors and assignment operators. So copy constructor. As mentioned before, what a copy constructor does in a shared pointer is that it copies, or like it increments the reference count while still pointing to the same memory location that the copied from object is pointing to. So what we want to do here is that pseudocode if actually it's basically going to be the same as C++ code, so might as well write C++. So if other dot mptr, so if other pointer is not null, what we want to do is assign the current pointer to others memory pointer, and assign the ref count to So ref count is a pointer as well now to the other's ref count, and then increment the ref count, which is the important distinction between unique pointer and shared pointer. So we can simplify this a bit by, instead of checking all of this like here, what I can do is instantiate fields here by basically doing m pointers is other.m pointer, and ref count is other.ref count. And you can see, like, even if these two are null, it doesn't matter here. So like these two don't really have to be inside this if. But what does have to be inside the if is the increment of the ref count. So if we can simply check our own ref count by this point because it's instantiated now. If ref count is pointing to a null pointer, just increment the ref count. So again, to reiterate, ref count is now being shared across different shared pointer instances, and when a shared pointer is copied, all of the shared pointer instances are now going to see this new reference count. Now, I think a couple of people previously mentioned when I asked, oh, is there an issue with the current reference count, reference counting? Now the issue becomes that this code is not really thread safe, because if you have shared pointers on different threads, then like both the pointer and the reference count here are shared. Like the pointer and reference count here are shared objects, and I'm incrementing the reference count here. So if these shared pointers are on different threads, then this is not going to be an atomic operation. It's pretty simple actually to make this thread safe. We just need to use an stood atomic reference counting, but I'll leave that for a bit later. Just to not have too many things at the same time. But let's move on to the copy assignment before I do the copy constructor. Copy assignment is pretty. So the difference between assignment operators, it's quite an important distinction. And the distinction is that when we copy construct an object, then the current object that we are constructing is like, there's no state right now for that object. It's not a constructed object. But so the current object in copy assignment, the current object may also hold some state. So there was some object which was already assigning this other object to the current object. So we need to ensure that we delete the state of the current object correctly. So in order to delete the state of the current object, I need to again do the similar checks that I did in the destructor, which is, oh, if the reference count is not null, then decrement the reference count. And if I end up decrementing the reference count and it goes to 0, then I want to delete my pointer and the reference count. So it's basically going to do all of these checks here again. So let's abstract this into a separate function. Let's call this, I think it's called reset in standard library as well. Yeah, reset replaces the manage object, which reset takes in a pointer, but you can see there's a reset without a pointer as well, which basically releases the ownership of the manage object. After this call, start this manages no object equivalent to shared pointer.swap. So it basically just does all of these checks and leaves the shared pointer in a state where it is not managing any object, and you can assign it to something else. So let's call reset here. I don't think I have reset defined here, so let me quickly do a reset. Ref count. Okay. Copy assignment. I'm going to do this a bit quickly. So copy assignment is simply going to be called reset. And then what we want to do is assign others object, like other objects pointed to my current one. So other.mptr, my ref count is going to be other ref count. And then again, if ref count is non-null, because it is possible that the others ref count might be null. If it is non-null, simply increment it. So very similar, like these three lines are very similar to what the copy constructor does. But the only thing, as I mentioned, in all the assignment operators, is that we need to ensure that the current state held by the object is cleared correctly. Let's see. Now we've got the other interesting constructor, which is the move constructor. Now the difference between move constructor and copy constructor is that move basically does not increment the shared state or the shared reference count, and instead leaves this. So what it's going to do is it's going to leave this other object in a state where it is assigned to null pointers, like the pointer is assigned to null pointer, and after other is moved from, it's no longer managing the memory. But this current object is now going to be the owner of the memory. So instead of incrementing the reference count as what a copy does, it kind of moves the reference count from this other object to the current object. So the current object is now going to own the same memory that the other object was owning. What it looks like in code is a bit similar to the copy constructor. All it does is it assigns the pointer to other.mPointer and assigns the ref count to other.ref count. There's one issue with this implementation. Does anyone want to take any guesses?
I think that maybe you are trying to get to the point that that move from objects should be, reset.
Yes, exactly. So we do want to reset the state of the move from object, this other object, but right now all it's doing is like the current object is the current object is now going to be pointing to the memory that other object was pointing to, but the other object is still pointing to the same memory, which is problematic, because if this other object goes out of scope, and say the ref count was equal to 1, now I have two shared pointers which have the ref count equal to 1, but other goes out of scope, and it's going to end up deleting the underlying memory. So we can do something a bit smarter here. I can use to exchange, which one sec. What exchange does is that it assigns null pointer to other.mPointer and returns what the original value was held by other.mPointer. So it's going to return what was originally held by this other.mptr, and ultimately I'm assigning that to my current pointer and assign null pointer to other.mptr. And I think it shows the red wiggly line only because I'm missing the library. I think it's in utility. Let's see if it goes away. Okay, nice. Move assignment really quickly. Again, the only difference between assignment and construction is that the state has to be reset. So going to reset the state, assign the pointer similar to before, where exchanged ref count. And I want to return. Actually, I did miss the return as well. So you can see the assignment operator returns a L value reference. So we want to return the current object. And that's it. Use count is pretty simple. All it does is if my ref count is not null, return ref count. Otherwise, return 0. Or actually, I can simplify this a bit by using the ternary operator. Yep. There we go. It does return long in the like a long type in the standard library. It seems use count. Yeah, so I would assume that the standard library actually stores the ref count as a long instead of an unsigned type. Pretty simple to change it here, so let's just do it. Okay. Before I move on to swap, I think I'll just add this access search so we can see this in action. I think it's been a while since been just writing this code. So don't have to worry about this, but basically it is a more safer way to write instead of t and, which is like instead of this, it's just a safer way to add L value reference on type t, because it could be a const which will remove actually it won't remove constants, but it will return a t constant in that case. Anyway, so this operator asterisk just gives me access to the pointer. So all I want to do is this is an unsafe access, so I think it does not do any safety check. So all I want to do is return pointer. So if it is null, this is going to access null memory, which is like undefined behavior. So this is an unsafe operation. And then this is simply going to give me access to the pointer. Get is going to give access to the pointer as well. And bool is a pretty simple check. It checks if like it's the operator bool, that is what enables us to do if my shared pointer, like if it's a shared pointer inside our if, that is what the operator bool allows us to do. So all it does is if the ref count or if my pointer is not equal to null. So been writing code for a while, so let's add some tests here, how it actually looks. This is pretty simple, which I already had. And it looks like there's already a compile type error on line 20. Long. I think it's complaining. Oh, there we go. That's nice. Okay, so no runtime errors. That's a good sign. But just to get some more visibility, let's print some stuff here. So let's call this make this class a bit noisy. Let's call this guitar. Guitar. Where's my copy constructor? And call this copy sign, no sign. That's included as stream here. Okay, this looks good. So we call once, which is where the SP1 is constructed. SP2 is copy constructed from SP1, so it calls copy constructor, and then both of them are destructed. We do need to ensure that this object that they're pointing to is only destructed once. So let's create a noisy object real quick, just to make sure that the object is only destructed one. And this is a pretty good way to debug things in C++, where you can create like these noisy objects and have like a quick and hacky check of how things are working. So let me do constructed noisy foo, and let me add a constructor. Call it Let's see. And we want to ensure that it's only destructed once. After all, the shared pointer goes out of scope. So change this to noisy foo. Oops. Let's see. Somehow the copy has copy and paste given up working somehow. Okay, so I'll live with it. Okay, so you can see copy. It constructed the noisy foo, constructed shared pointer, copy constructed shared pointer, destructed both the shared pointers, and only after that the noisy foo is destructed. Quick move construction as well. I won't go into like too many tests for this. I'll share it on the slides because I do want to talk about make shared, which I think is quite an interesting piece. But you can see now with should move, what it does is it constructs noisy foo, constructs my shared pointer, move constructs my shared pointer. Then there's a detour. It's a bit different to the previous output. In the previous output, there were two destructors, and then the noisy foo was being destructed. But in this case, what's happening is that there's a destructor for like my SP2 destructor for the SP1 object. And then actually sorry, let me see if it should not be the destructor of SP1 object, it should be the destructor of SP2. We can probably do something like this where it's not a so I'm showing some ways on how to debug things like that. What we can do is have a static variable here. And static variable are associated with the class. So we will know which of those is being destructed. And I don't think we need things here. So it says, and then I want to move constructor. M on identifier Quant. And then let's do constructor as well. Only if I can find it. Move constructor, move assign, move constructor. Okay, so I've got constructed noisy foo, constructed the first one, move constructor. Oh, it makes sense now because I'm moving from the first one. So, okay, so the second one is destructed. It says destructed 2. And then obviously it's going to destruct noisy foo because noisy, that's the important difference now. So if you look at the previous output where it was copying, let's have a quick look at the previous output. You can see it creates noisy foo, constructs, and then it destructs both of them before it destructs our actual object. Because now there's 2 pointers pointing to noisy foo. But if I move it, now SP1 is no longer pointing to that memory. So that does not need to be destructed before noisy foo is actually destructed. So you can see it only destructs the second one, SP2. before it disrupts noisy foo, and then the first one can be disrupted. Does that make sense? Does anyone have any questions around this behavior? Okay, if not, I did want to talk a bit about shared pointer, but I think since we've run out of time, what I'll do instead is that I'll write a post about what's interesting in shared pointer, and just to give like a sneak peek, make shared. Make shared is pretty similar to make unique, where it's like a free function which you can use to create shared pointers. A very simple implementation would be something like a very simple implementation would be something like this, where you it takes all these arguments. Again, you don't have to worry about templates, but imagine these are all the arguments to construct a pointer to type T. So a very simple implementation of this would be T star PTR new T, and just don't worry about the templates for now, for a second, and like let's flip forward and stuff like that. But all it does is that takes in these multiple arguments. This implies that it's like a set of arguments. It takes this set of arguments and passes it on to this call. Now that we've got a pointer to type T, what we can do is we can return a shared pointer of type T with that pointer. Now, this works great. It's like a decent implementation of make shared. All it does is that it takes set of arguments which can be used to construct a type T. So instead of passing a pointer which is already constructed, you just point the set of arguments, and then it returns your shared pointer. There is one downside of this though, which is again pretty important in performance critical environment. And the downside for this implementation is that on line 124, you're doing a heap allocation, and then on line, like when you end up creating a shared pointer, we discussed before that this construction with a pointer leads to a heap allocation here on line 22. So what ends up happening is that there's one heap allocation for the object on line 124, and then a second heap allocation for the reference counting when you create the actual shared pointer. So there's two heap allocations instead of one like bigger heap allocation, which is usually worse than simply one allocation, because a single call to allocate memory will be a single system call. Both of like the memory allocated will likely be adjacent to each other instead of being spread across in the like virtual table. So it's usually a better idea to do a single memory allocation call. In this case, because it's allocating pretty small memory. So there is one downside for this, and it's pretty interesting to see how this is overcome and what the implementation for that is. But since we're running out of time, what I'll do is I'll write a like blog post about that and attach it on the LinkedIn page. But I think that's it for today. Thanks so much for joining. If you did have any questions, I'm happy to answer them. And I'd really appreciate it if you can fill in the feedback here. I'll bring up this slide again, but just a quick note. I got a feedback last time that it would be nice to have some resources. Type erasure is, so I've added this slide, and the reason I have type erasure here is that a more advanced implementation of shared pointer uses type erasure, and I'll probably just end up writing an article about that. So it's pretty interesting. Like this technique is one of my favorite things in C++, and it's extremely commonly asked in like interviews and if you talk to people in trading firms. So this is a pretty good kind of, it's like a design concept in C++, so it's a pretty good one. And just a quick note on what's coming next. So I'm pretty keen on doing a session on log-free programming, cache alignment, and fault sharing. These are areas which I'm quite interested about, and people also mentioned in the last feedback that things like this would be good to cover. The next thing I'm keen is on a session on C++ 26 contracts. And I think once we get about 20, 30 people who are actively attending these sessions, we can get speakers from different firms like Citadel, Jump, HRD. But yeah, I think we need a critical mass of people before that happens. So if you have like friends interested in C++, please like ask them to follow the page on LinkedIn and bring them along with you next time you come. But I'll leave it there. And if you have any questions and or feedback, I'll really appreciate if you can fill this form. Thank you so much.
Thank you.
Thank you.